Our discussion on properties of cut sets. And in this video we are going to prove this statement. The proof is similar to the proof of the statement that we discussed in the last video. So here the statement it reads as follows. So with respect to a given spanning tree T and a branch Bi, okay, and this branch Bi determines a fundamental cut set, say S. Okay, this Bi is contained in every fundamental circuit associated with the chord in the cut set S. So we have this cut set. Okay, so this cut set contains a branch edge, the fundamental cut set. So it contains exactly one branch edge and one or more chords. So that says this Bi is contained in every fundamental cut set, fundamental circuit associated with the chord in the cut set S, in this cut set S, and no other. Okay, so to get an understanding of this statement, let's look at an example. So let's fix this Bi to be equal to E5, this branch edge. Okay, so let's consider this graph and this highlight in green spanning tree. So T is this spanning tree. Okay, and let's fix Bi to be equal to E5, okay, this branch edge. Okay, and the cut set, the fundamental cut set S, okay, that is determined by this E5 will be, okay, E4, E5 and E6. Okay, E5, E4 and E6. So this will be this fundamental cut set determined by this branch edge, okay, E5. And the statement says Bi is contained in every fundamental circuit associated with the chord in the cut set S. So if you look into this particular fundamental cut set, E5 is a branch and E4 and E6 are chords. Okay, and here this corresponds to the fundamental circuit corresponding to this chord E4. So that circuit will be like E4, E5, E3. Okay, E4, E5, E3. And the fundamental circuit corresponding to E6 will be like E6, E5, E7. Okay, so we can see that, okay, this Bi, it appear in F1 and F2. Okay, contained in every fundamental circuit associated with the chord in the cut set S. And again, we can see that if you look into any other circuit, fundamental circuit here, another circuit will be like this thing. We can see that, okay, E5 it does not belong to this circuit. So similarly, E5 it does not belong to this circuit also. Okay, and I think there is, okay, so those are the only fundamental circuits. So we can see that this statement is true for this example. So let's go and prove for the general case. Okay, so let G be a connected graph and a T be a spanning tree of G. Okay, so let Bi be a branch edge with respect to this spanning tree T. Okay, and let the fundamental cut set determined by, okay, let the fundamental cut set determined by this Bi, okay, determined by that branch at Bi, B is a S, which is equal to, so it contains this branch edge along with 0 or more chord edges. Okay, and let suppose that we have say P chord edges, okay, which consists of P chord edges, okay, P chord edges and this branch edge BI, okay, which consists of P chord edges and the branch BI. Okay, next what we are going to do is we are going to look at the fundamental circuit determined by this CI, and we know that every chord uniquely determines a fundamental circuit. So this C1, it uniquely determines a fundamental circuit, similarly with C2 up to CP. Okay, so we know that every chord uniquely determines a fundamental circuit. Okay, and let F1 F1 be a fundamental circuit determined by C1. Okay, so and let it be say C1. So a fundamental circuit will contain a chord and the branch edges. So let the branch edges be say B1, B2 up to say BQ. Okay, be the fundamental circuit associated with with C1. Okay, consisting of Q branch edges. Okay, consisting of Q branches and the chord C1. Okay, so here we can see that this C1 is in both S and F1. Okay, so that C1 is in both F1 and S. So, okay, so we know from my previous theorem that there must be an even number of edges common in a cut set and a circuit. So that says there will be there must be one more common edge in F1 and S. Okay, so that says this C B1 must be equal to so B1 must be equal to this thing, because these are branches and we have only a branch here, and we know C1, these two are equal, C1 is common to both, so that says some more other edge must be same. Okay, so that says this BA must be equal to one of these B1, B2 up to BQ. So as there must be an even number of edges common in a cut set and a circuit, there must be at least one more edge common to okay, F1 and yes, okay, but among the remaining edges in F1 and yes, only a branch can be common in both. Okay, so here we have these branches. So C1 is common to both F1 and yes, and since there must be an even number of edges common in a cut set and a circuit, okay, so we have a branch here and every remaining thing other than this C1 is a branch. So that says that BI must be equal to one of these. Okay, so but among the remaining edges in F1, and that fundamental cut set is only a branch edge can be common in both. Only a branch can be common. Okay, so therefore BI is one of the okay, so BI must be equal to one of the branches B1 up to PQ, B1 up to BQ. So that says BI is contained in the fundamental circuit F1 corresponding to chord C1 of S. Okay, so therefore this BI, okay, it is contained in the fundamental circuit F1 corresponding to, okay, this is F1 corresponding to chord C1 of yes. Okay, so B1 is contained in the fundamental circuit F1 corresponding to the chord C1 of S. Similarly, we can see that so B1, this BI, it is going to contain in the fundamental circuit corresponding to chord C2, C3 up to okay, chord C1, C2 up to CP. So that says B1 will be common to all those fundamental circuits. Okay, so exactly the same kind of argument holds for the other chord edges. Exactly the same argument holds for the fundamental circuits associated with C2, C3 all the way up to CP. Okay, C1, okay, C1, C2 up to CP. Okay, so we proved this particular thing. BI is contained in every fundamental circuit associated with the chord in the cut set. Okay, but we have to prove that so BI is not going to appear in any other cut set. Okay, so therefore the branch edge, okay, BI is contained in every fundamental circuit associated with the chord edges in S. Okay, so let's go and prove the other thing. Okay, this BI, it cannot appear in any other fundamental circuit. Okay, so moreover, we can see that if the branch BI is in any other fundamental circuit, say F dash in any other fundamental say F dash in T, okay, besides those associated with the chords C1, C2, okay, I think no need to consider this one anyway, because C2, C3 up to CP, okay, then there would be only one edge BI common to both this F dash and S. Okay, and the reason is since none of the chords in S are in, okay, none of the chords in S, since none of the chords in S are in F dash. Okay, but this is not impossible because there must be an even number of edges common in a circuit and a cut set. Okay, and that says this BI, it is not going to appear in any other fundamental circuit. Okay, but this is not possible as there must be an even number of edges common in a circuit and a cut set. Okay, so we are able to prove two things. So BI is contained in every fundamental circuit associated with the chord in the cut set, and we are able to prove that BI, it is not going to contain BI is not going to contain in any other fundamental circuit, okay, other than those determined by the chords in the set S, cut set, fundamental cut set S. Okay, and okay, so that's the theorem. So we can see that BI is contained only in the fundamental cut set corresponding to the chords of the fundamental cut set determined by BI. So BI is contained only in the fundamental circuit corresponding to the chords of the fundamental cut set determined by the branch at BI. Okay, and hence the proof. So we are able to prove this statement with respect to a given spanning tree T and a branch BI. Okay, that determines the fundamental cut set S. Okay, BI is contained in every fundamental circuit associated with the code in the cut set S, and BI is not contained in any other cut set other than these fundamental circuits associated with the code in the cut set. Okay.